morning, we have 4 lectures with plenty of time. Our first lecture is given by Professor Jiangsu Xu from Western University, Canada. Professor Xu, please.
Okay, thank you, Professor Fang. First of all, I'm very happy to be invited to give a presentation on my research. And also, I'm also happy to serve as a co-host together with Professor Zhang and Richard and another professor in for this conference. So this is my honor to give a presentation on my recent research on the bio-based materials, particularly produced from wood, natural wood, for structural applications. Can you see my slide, everyone?
Yes, we can see.
Okay, that's good. So before the presentation, I just want to briefly introduce a research program we started last year. So we call it Consortium for Industry Bioproduct Innovation, Western University. So this consortium started last year. Target is to respond timely to the Canada's goal to achieve net zero emission by 2050. This net zero emission, I think every country, most of country in the world target to achieve by 2050, or some country, for example, China, want to achieve that 2060. So this is one of the major target every country adjust the CO2 emissions. So our research program started in last year is about the bioproduct, industrial bioproduct. Some product produce a bio-based product from the renewable biomass, including forestry and agricultural biomass. We have a theme. We have 5 themes in the program. So including some theme on the engineered adsorbent catalysis, and also bio-based carbon, biodegradable or bio-based polymer, and biomaterials for agriculture and greenhouse industry, and as well as for the economy analysis, technical economy analysis, and life cycle analysis as well. So we have 5 themes in this program. The program is based on the industry collaboration. So we have a list of almost 16 industry partners in this program. They will provide the research idea and the funding. And we will collaborate with the industry partner to solve some particular target research. For example, develop some new product, bio-based product for the industry application. So this is about our industry members. Back to our lecture, back to our presentations, I want to briefly introduce some of the research motivations, why we want to target wood-based biomaterials. First, wood is not a new materials. People used wood for a couple thousands years, actually. If you look at some very ancient wooden structures, architecture in China, so the Chinese people build the wood structures in a very professional way, and they can make a very tall structure like this in these pictures. And the wood is also still using as a structural materials in North America for house constructions. And in the past several years ago, actually, so Canada actually achieved a highest or tallest wood building, 53 meters high, on the campus of UBC in Canada. So they built the world tallest building in wood structures. So this is one of another application of wood for structural applications. But if you look at the wood structures, the applications in the industry, actually, they do not use the wood directly. They produce the engineered wood. This engineered wood, including a family of different type of wood, for example, plywood, medium density fiberboard, and also medium density particle board, OSB, oriented strand board, and also LVL, laminated veneer lumber. So those engineered wood has advantages compared to natural wood. This engineered wood has a dimensionally stable, so they have the more uniform properties, dimensionally stable, and also they can utilize some of the wood waste, for example, chips, sawdust, and some other materials from forestry industry, as well utilize the biomass from the agriculture industry, for example, the crop residues. They can produce the engineered product from different type of waste materials. The wood actually, so if you look at limitations, so there's some limitation. If you want to use the wood for structural application, the wood normally has a poor water resistance. They can absorb water, and also wood is not good for the fire resistance, and also not good for the mold resistance. So this make the wood have some challenges if you want to use this for structural application. But the engineered wood actually has improved the strength. If you look at the table on the left, so this table shows the engineered wood compared to steel. The steel for the tensile strength normally can achieve 400 megapascal. But engineered wood, for example, LVL, they can achieve about 10%. Okay, compared to the others. So, for example, the MDF or OSB, they are relatively less strength in terms of tensile strength. So, for engineered wood, so the reason for using engineered wood is to overcome some limitation of the wood-based materials, to improve the strength, fire resistance, and some anti-mold property. So that's why the engineered wood has gained more application in the structural application, in the wood, in the house construction, or in other structural applications. Wood as natural materials. Wood-based natural materials, actually, they have unique property. If you look at the wood structure here, they have unique hierarchical structure. Hierarchical structure is you can look at the structure, they have very nice aligned pores. And we can do multiple modification to convert the wood to different materials. For example, we can do carbonization to make carbon for electronic applications, and also we can turn wood to a transparent wood for some construction, for window applications, as well. So we can turn wood as an absorbent for environmental applications. For sure, we can make wood as a structural application to densify the wood after densification. So wood actually has multiple applications because of the unique structures. For energy efficient building, so this application actually recently published by some of researchers in the US. So they can make wood transparent. And this transparent wood can make a transparent window for energy efficient building. So this is for window applications. For this application, actually, if you look here, so the window normally is a glass materials. But if you make a wood-based transparent materials, then this has a better property. They can provide a better light distribution through this transparent wood-based materials, and also can serve as a thermal insulation materials. So they can regulate the temperature of inside in the room, and also they can be modified to get an additional tunable property, to add some of the functionality to absorb the formaldehyde, and that's another applications. So this make the wood-based materials more useful than glasses for window applications. For environmental application, people are still under the research. One example is that people actually won publications from 2019. So they load the several nanoparticles into the wood, and then turn this wood as a filter to remove the water, the pollutant, for example, E. coli, some bacteria, as well as some methylene blue, the color for textile water, wastewater, they can use this for the water treatment and heavy metal removal as well. So this make wood as one of the interesting absorbent for environmental applications, particularly for the wastewater treatment application. For structural application, people actually they explore different scale of application. From the macro scale, from the meter scale, macro scale, down to the nano and molecular structures, molecular scale. So this different scale of provide different properties. For the molecular scale, the wood can inside the molecules of wood, they have lots of hydrogen bonding. So can strengthen the wood. If you can improve the hydrogen bonding, then we can make the wood more stronger for structural application. For nanoscale, they have aligned nanofibers, microfibers. So those actually provide a very strong strength property for wood for different applications. In terms of the structural application, we have one strategy, which is commonly used by many scientists or by many industry now. So this strategy is to remove the lignin first. So to extract the lignin, remove lignin, then open the pores. Then to densify these fibers. So after lignin is removed, the wood become porous, and then densify that to make a very condensed fibers. And after densification, this densified wood, provide a strong property, strong strength. This actually has been reported by a US group led by Professor Hu in Maryland University. So they published several very excellent work in Nature or in Science. They produce a different type of high performance structural materials after removal lignin and then after densified wood. So if you look at this figure here, so the wood specific strength means the sum of the strength, tensile strength divided by the density. So it's a relative strength. And this relative strength is much stronger than most of the metals. For example, aluminum alloy, stainless steel. Actually, they are weaker than this densified wood. So which make the wood is stronger than the metals from their research. Still from their group, so they report this strong wood materials in terms of the tensile strength and versus the density. So the tensile strength alone, if you look at here, so tensile strength, the wood, they have densified wood in this circle here. And many alloys, for example, aluminum copper alloys and the nickel alloys, they're actually in the same level of strength. But density, wood is significantly lower density than the metals. So this make wood is a high highest strength and low density. So this can gain lots of application in the transportation industry. For example, we can produce a lot stronger and lighter materials. And for the aircraft industry, so this can make a more energy efficient structural materials. They can reduce the density. And this table also compare the flexural strength, which is a bending strength. Okay, so this flexural strength of densified wood actually much higher than the stainless steel, almost 3 times higher, and almost equal to the some aluminum alloy. So this show another aspect. So this wood can be stronger in terms of flexural strength, bending strength. But the challenges. So we actually nothing is not perfect. It's still under investigation, under research. So some of the common challenges that the processing time is very long. If you look at Professor Hu's research in published research, they remove lignin and then densify the wood. They almost take more than 24 hours processing. So it's a long time, long processing time, which make this industry application difficult. And the waste lignin is not utilized. So the lignin is just removed, but without utilization, this is another kind of resources we should utilize. And the resin, they they do impregnation of resin into the wood after remove lignin. But this resin mostly produced from petroleum-based resin. For example, petroleum-based phenol-formaldehyde resin, petroleum-based epoxy resin. So, but how to solve these challenges? How to address these challenges? That's our research motivation. So we want to address that. So to overcome the long processing time, to utilize the lignin, and then to avoid the use of petroleum-based resin. So our research objectives, as I said, so to address those challenges, so we do the we extract lignin first, same. So but with our lignin extraction, actually we extract more efficiently. We use ultrasonic, so we can make the extraction more efficiently to remove lignin and then make a porous delignified wood. And then we turn the lignin extracted. So we use the same lignin from the wood and then convert that to epoxy resin. So after we produce epoxy resin, then we impregnate that resin back to the porous wood, so we can make a composite. Composite in the lignified wood with the lignin-based epoxy resin. So in this way, we address those three challenges. Okay, so in our research. Then we produce a wood-based composite, so we can look at the how we the overall process and then the property of the composite we produce. So this slide shows the overall process. So we do the delignification, remove lignin, and then we turn the wood, natural wood, to a porous structural wood. Then the lignified lignin, we do the conversion. We convert the lignin into epoxy resin. Then we do the composite. Okay, so we impregnate this lignin-based epoxy resin into the delignified wood, and then we do the densification, pressing, hot pressing, to make a composite. So that's their final materials. This material is derived from the original, from the natural wood. So we want to compare the property against this original wood. So we call this process, we call it re-engineering. Re-engineering, the idea is that we do the engineering first. So we separate the component first, and then we do the conversion, another engineering. Then we do the composite back. So this is another engineer. So we call this re-engineering approach to make our target to make a more stronger materials and a lightweight. Okay, so this is the overall idea for this research. And this slide shows this the morphologies. So natural wood with 70% of wattage porosity, and after remove lignin, we improve the porosity to 80% after remove the lignin. And then the lignin content reduced from about 30% to about 5%. So we significantly remove the lignin using the ultrasonic assisted organosolve method, using some organic solvent to extract the lignin. And this is a lignin properties after we do the characterization, for example, molecular weight and purity, and the epoxy content after we turn the lignin to epoxy resin. So we list it here. So in terms of molecular weight, our lignin, original lignin has that molecular weight, a number average is about 1,000. Okay, and then we turn to epoxy resin. So this molecular weight does not change too much. Epoxy resin just epoxidify the lignin function group to introduce the epoxy group into the lignin structures. And the water resistance. So after we produce this composite material, we compare the water resistance to the natural wood For example, natural wood can absorb 60% of the water in 24 hours. But our epoxy resin impregnated composite, so we can reduce the water absorption to less than 10%, 15%, or 60% after coating. After coating the surface with the same epoxy resin, so that's coating. And compared to the commercial epoxy resin, wood composite, so almost similar level of the water resistance. And the thickness swelling is also controlled to a very low level, thickness swelling. And the width increase is how much expansion, so much expansion of the wood. So this also control very low level. So we can make this wood composite very high resistant to water. Another property is about the water contact angle. This water contact angle is just to check the surface morphology, the hydrophobicity. So we can include the water contact angle from 0 degree to almost 90 degree. So this surface is almost hydrophobic compared to original natural wood. So we make this material is hydrophobic. That's why this material has high resistance to water, as we shown before in the previous slide. And for flame resistance or for anti-oxidation, and this test was done by using the oxidation induction time, oxidative induction time. This is show how much time, how many minutes this material can withstand the high temperature in the air without catching on fire, without oxidation. So if you look at the peak here, the peak exothermic peak means some oxidation happens. So the longer time to show the peak, the better flame resistance property. So we show that for compared to natural wood can be oxidized or can be ignited within 2 minutes, 1 minute. But our wood-based composite with the lignin-based epoxy resin, so we can elongate that time to about 3 to 4 minutes. And also the peak area, this peak area shows how much heat release, how much oxidation heat. So this peak area is much smaller than compared to natural wood, means that the oxidation reaction is much suppressed. So by this composite, so by this wood-based composite materials. So that's another good property in terms of application. So which means has some fire resistant property for this wood-based composite materials. And this slide shows the fracture strength. Fracture strength is how the bending strength for the specimen. So the wood-based composite materials with the lignin actually with our materials. So this actually almost gain 8 times higher the fracture strength compared to natural wood. And also compared to wood-based composite using petroleum-based bisphenol A-based epoxy resin, our lignin-based composite actually achieve more fracture strength compared to the commercial epoxy-based composite. Similar for tensile strength. Our material is shown here, so it's almost 4 times higher the tensile strength compared with natural wood, and also much stronger than the commercial epoxy resin-based composite. So this is another property demonstrated by this new materials. So our lignin-based the epoxy resin composite with wood actually achieved a very higher tensile strength and fractural strength. So now we put our data here. This is a star here. This is our work compared to other work. Compared to the other work, they measure the property. For example, the titanium alloy, aluminum alloy, steel, in terms of specific module, and also specific strength. So this specific means relative. So the strength divided by density. So our new materials has much stronger stronger specific strength compared more than higher than any other metals and other arrows. So this, and also because of the lighter weight, so this make this is more superior to the metal arrow. It's stronger and also lighter. So now we achieved our target. Re-engineer approach, actually, we obtained the highly strong materials and lighter materials, and also our process is better than a literature process. We do not have a lengthy lignification step, and we do not need to do densification for a long time. Our time is only minutes. So compared to 24 hours in the literatures. So this actually makes this process more advantageous than the current state of art. But for chemical resistance, there's another property we tested. So in order to make this material more useful for some application, for example, for some ship structural materials for in the ocean, they have a sodium chloride. And for some of the application, they may have some sodium hydroxide, the alkaline condition, or some acidic condition, HCl, hydrogen chloride. So for those application, we test the resistance. After you merge the materials in those media for 24 hours, and then we do the tensile strength test again. We found that this material, this composite, has good resistance to sodium hydroxide. So because the strength did not reduce significantly, and also have a good resistance to sodium chloride and water as well. But for hydrogen chloride, the acid condition actually reduced the strength significantly, almost to half, 50% loss. So this makes this material may not be suitable for acidic condition. For some reason, we do some investigation on that. So why this happened for this acid condition can make this material actually lose intensity, lose the strength. So we do some of the XRD analysis. We show that after we do the HCl and sodium hydroxide, the structures, actually if you look here, compared to original natural wood, the crystallinity reduces. That's probably one reason. They become more amorphous, so they lose crystallinity. This could be one reason contribute to the strength reductions. In addition to the crystallinity, we also try to explain better about the mechanisms. Another mechanism is about the internal tension. Because for the original materials, because epoxy resin and wood, after curing, we add some of the amine to cure that. So this amine actually they can repulse each other. They create some internal strain, internal tension inside. But if this material is in contact with the HCl, the hydrogen chloride, they create some of the electrostatic force within the materials. They have attraction force. This attraction force we are balanced by balance some tension. So they can actually overall tension reduces. The overall tension reduction actually will reduce the strength, because the tension enhance the strength. So that's about the materials, the reason. So in material science, the explanation. So why the HCl will reduce the strength of these materials. So we just conclude that this materials may not good for the acidic condition, but they could be a good resistant to other application for water or for sodium hydroxide or sodium chloride. The conclusion is that we achieved this novel process to produce stronger and lighter materials, and we can use that for many applications, for structural applications. And compared to compared to the literatures, we solve this, we address this as challenges, and we make this process a shorter time and then we utilize lignin, and we would use a petroleum-based resin. Finally, I want to acknowledge the funding support from different sources, including the government of Canada and also the industry support, as well as the university support. Thank you for your attention. So I'm stopped here. If you have some question, maybe we don't have time to do the question, but if you have, so you can ask the question. Thank you.
Professor Xu.
Yeah.
Okay, please.
Yeah. So any questions?
Okay, Professor Zhu, I'm Sarani again from UKM. Great honor to meet you. I was graduated from Canada also. I just want to ask you, when we know that lignin is very unstable, tend to polymerize and so on and so forth. When you try to extract lignin from the wood, and we know that most of the lignin, 100% of lignin contains in the middle lamella and high proportion in secondary wall. But when you extract the lignin intensively from the wood, how do you make sure that the cell wall structure is not collapsed because of it is glued by middle lamella from one cell wall to another? That is my first question. The second one is that we know that lignin in the natural form and lignin from the extraction is totally different lignin. And how do you handle this to make sure that you will be able to form a good epoxy resin during the modification and so on and so forth? Thank you.
Yeah. Okay. Yeah. Thank you for the questions. First, the question is the extraction lignin, how to avoid damage to the cell wall, right? So in this research, actually, we use ultrasonic. And we use a milder condition for the organosolv extraction. We use a temperatures below 100 degrees C. So try to avoid damage to the cell wall structures. Only extract the lignin out, assisted by the ultrasonic, the shaking, ultrasonic agitation. So that's the one approach we used. In terms of the epoxy resin, so for this lignin, actually, we do modification. We do using phenolation. So we modify the lignin using phenolation, and then we improve the lignin activities. So we can get a epoxy the index content is more than 10, so which is highly epoxidized the lignin. So we make this lignin as more useful for application for structural applications.
The other question is how is this the difference between one species to another, because of each of the lignin is not similar, even in the same wood. In a different wood is even worse because of your H, S, and G is totally different. So how do you handle that?
This could be very good questions, because in our research we use the softwood only at this moment. We do not test the other type of wood, but I suspect that the different species of wood have different structures and morphology, different structures, different lignin content and cellulose content, so they could perform differently. So we need to do more testing on different type of wood. Yeah. Okay, so we may have probably be the time is almost here.
Hi,
so for next presentation, yeah, if you have questions.
Hi, Professor Charles. Hi, Professor Charles. I'm Bing Song. Can you hear me?
Yeah, I can hear you.
Yeah, I'm Bing from New Zealand Forest Research Institute. I've been following your study since 2014 or 15, I reckon, and for years. And yeah, because your in my understanding that previously your research has a strong focus on converting biomass for producing biofuels.
Yeah, we still do that.
Yeah, you have done some great researches in hydrothermal liquefaction of biomass for biocrude production and also biomass pyrolysis and stuff. So yeah, during my following, only recently I started to notice that you are now shifting some, like what call it, some of your focus to do biomass based materials.
Yes.
Yeah, because I think you've already built up a great reputation in the area of biofuel. So what I'm curious as a scientist, I'm curious about like your motivations of doing this what you call it, like a transportation or transformation. So what are the motivations from your side? Yeah.
Thank you, Ben. Yeah, first of all, actually, so this is a very good question related to why we've just switched to some focus for other stream of research. The biofuel actually still our focus. So we still do lots of research on hydrothermal liquefaction, but we do some of new research in the bio-based materials, because compared to fuels, the materials or chemicals is more valuable. And also many industries that are looking at green-based chemical, green bio-based materials to address the carbon emission problem. So, and because it's more value added, so we have more industry support to do this research. So that's why we split our research strengths to direction to several different paths. So biofuel and also bio-based materials. So we do not drop the biofuel. Biofuel is still our research. Yeah.
Cool. All right. Thank you. I look forward to seeing more of more interesting studies conducted from your group. Thank you.
Thank you. Thank you.
Professor Xu, very nice talk. Maybe now, can you hear me, Professor Xu? Professor Xu, can you hear me? There's no voice.
I think you muted yourself.
I'm mute. Okay, sorry, I'm mute. So now you can hear me, right, Professor?
Yes, I can hear me. Maybe the time.
Yeah, the time to do the next.
Maybe just the last questions for you. I think someone is asking you. Okay.
Okay.
Then you go ahead. Okay.
Okay. So next question. One last question, if you have.
Yes, Professor Xu. I thought I have no time. It's just a quick question. So I'm very curious about your densified the wooden structure material that have even stronger strengths comparing with alumina alloys. And that's very interesting. So you dense the pore structure and make it stronger. So I just wondering, because I previously I have some experience when doing carbon forms, I found that the large micropores have a bad effect on the strength, but on the other hand, the macropores, or even the mesopores, are very interesting. Their appearance will even contribute to the strength of the material. So I'm wondering if you have some study on the pore size or the pore size distribution on the effect of them on the strength of the wooden material. Thank you.
Yes, sure. This is a good question. But all materials before densification, we already impregnated with epoxy resin. So the pores are filled by the resin, and we compress them. So the pore structure is not there. It's already filled, impregnated with a resin. So we do not have the micropore or macropore effect. We only compress the composite together.
Okay.
Did I answer the question?
Yeah, okay, thank you so much. By the way, I'm from Professor Fangjin's group. Thank you.
Good to meet you, yeah. Okay, thank you for all of you for the questions and the interest, so we can communicate after the presentation. So if you have some question, you can still communicate by email, okay? Okay, so time is ready for next presentation. I want to give a brief introduction about next speakers. Professor Sarani Zakaria is from the National University of Malaysia. Let me just stop my sharing here. Okay. And Professor Zakaria's research is mainly focused on the pulp and paper and the wood plastic composite, as well as the cellulose derivative research. She published a large number of papers, more than 200 papers already, and including 12 chapters, book chapter, and 6 books, which is very impressive in the field of utilization of the plant biomass for high value added products. So I'm going to give the time to Professor Zakaria to present her work. Okay, so Professor Zakaria, you can share the screen and you can start your presentation.
Can you see the screen?
Can
you see my presentation?
I do not see the screen now. I'm not sure if other.
Let me try to share it.
Yeah.
It was okay.
We also cannot see the screen.
You cannot see that, so not yet.
Okay, let me see if I can get it from my.
There is a small arrow, up arrow. You just click, then you can share your screen.
Top right.
One moment. Click right. Share. Yeah, I put it to share. It is like.
Click your screen.
Let me try to share. This is my screen. Okay, can you see it?
Now I think it's not yet, still not yet.
Yeah, can you see?
Yeah, we can see it. Yeah, we can see the screen.
Okay, thank you very much, Professor Zhu. It is a great opportunity for me to be given to talk to this particular conference. So I think my research is almost similar to Prof. Zhu as far as the liquefaction is concerned. So today I'm going to talk on the liquefaction catalyst properties on liquefied knauf polyols, where I make a comparison with knauf and also all palm anti-fruit punch because this is the most abundant biomass in Malaysia. So looking back to the biomass, there are many types of biomass, and now they try to categorize biomass into about 6 categories by giving them colors. Okay, the first one. Let me see if we can get a pointer presenter. Okay, point option. Okay. So the first one, they categorize as a yellow biomass, which is involved of agriculture, forest waste like straw, wood chips, anti-fruit bunch, coir, bagasse, and so on and so forth with agriculture. And the green biomass is a green grass, foliage, and stem. For example, like leaf, trunks, branches, and root. And they also concerned about the blue biomass, which is a lot abundant from the fish processing cut off seaweed. From, for example, alginate, carrageenan. We are working a lot with these particular materials because of they have a very good antibacterial properties, and at the same time, a good carrier as far as pharmaceutical is concerned, drug carrier. And red biomass is come from slaughterhouse waste, blood, and cut off. Okay, this is lots of proteins, and the some has been used this red biomass as an adhesive for adhesive, for a glue, and so on and so forth. And the next one is a gray biomass for agro-industry side stream, the waste from agro-industry. And finally, brown biomass, which is from sludge, manure, household waste, and so on and so forth. So to show that we have so much of this biomass material.
I just interrupt. You didn't share your screen. You just upload your slide.
Okay, I cannot say.
I do not see the transition. Do not see the transition of slide. The slide is still in the first page.
Let me see it again.
Yeah. I thought it's my computer problem. Probably not. It's just the.
Let me.
Can you go to the presentation mode? Then you can click the next slide to check whether it's normal.
Let me say. Okay, this is the presentation mode. Okay.
This is the presentation mode. Okay. So then you can make a transition. Next slide.
Okay, next slide.
That is shown. It moves.
Okay.
Now.
Okay then. Okay. So we have gone through the full potentials of this biomass. Save it. Okay, so for the mine big data, you will notice that lots of there are big words here, but natural fiber has been one of the major contribution as far as research is concerned compared to others. Lots of, if you compare to synthetic fiber and glass fiber, so the natural fiber is huge as far as research is concerned nowadays. And in Malaysia, we are like China also, we are in tropicals area. Lots of green and yellow biomass, which is, for example, like all palm fiber. We cultivate quite a huge amount of area of plantation for palm oil, where you have lots of fronds which can be collected every day, the trunk, and also the all palm anti-fruit bunch. We also grow quite high, huge amount of rice plantation in the northern and also in the eastern part of Malaysia, where we grow lots of rice, and we have quite huge amounts of rice straw, and we have sugarcane and pineapple leaf, especially in the northern part, the southern part of Malaysia. And this is not being utilized. Every year after they cultivate, I mean, they harvest to get the fruits, and the leaf is left unattended. And the new one, which is Knaf, has been promoted by Malaysian government to help the farmers for the fast-growing crops. We call it Knaf, where you can harvest within 3 months' time. And in the eastern part of Malaysia, in Borneo, they have like lots of sago to from the sago trunk, so that they can make a sago starch. And you have lots of sago which contains high proportions of cellulose. And like in China, you have cotton, we have kapok. The proportion of cellulose also high in kapok, but the only is a waxy material is very high, and lots of wood waste. And back to Knaf, it is a very fast-grown species. As far as Knaf is concerned, by 3 months, 2 to 3 months, you can harvest Knaf, where you have the bast fiber, the outer layer of the Knaf stalk, can give you a very good high proportion, a good proportion of fibrous materials, where the core one, which is very, it absorbs so much of moisture, very hydrophilic, and has a very high pore structure, and been utilized a lot for low-end use. For example, maybe for oil spillage, and maybe for animal beddings, and so on and so forth. So for that, for those who are working in composite material, the bast fiber has been used a lot. As far for the textile materials, weaving it together with the polymer, and then press it to make into a very good composite, high for automotive and for other application. And the Knaf has been introduced in Malaysia since more than 10 years back, where lots of states, many states in Malaysia start planting Knaf. And the northern part of Malaysia has been focusing on productions of seed as far as Knaf is concerned. And they are trying to increase more area for Knaf plantation because of the urge for the bast fiber is higher. But then the core part is not being utilized, but there is a high proportion, about 60% of Knaf core, which is not being utilized because of the short fiber. So that is the reason why we thought that this is a good thing to convert this particular Knaf core into high value added products. Like all palm fiber, if you go to Malaysia, you fly through Malaysia, you will see many areas has been green, has been cultivated by this particular all palm fiber and all palm tree. And after 5 years, the trees start growing the fruits, giving you fruits. But the fronds, they have to cut down the fronds, pruning it almost every day. And the best fiber is from the fronds. But then to collect the fronds from the palm oil plantation is very costly. And the fruits, once you remove the fruits, you're left with anti-fruit bunch. And this empty fruit bunch give you quite a good, if you shredded it, can give you quite a good high proportion of fiber, about 20% to 30% of a good fiber is coming from this empty fruit bunch and has been utilized for pulp and paper, composite materials, for beddings, and also for landslides and so on and so forth. And this is also, we have like for palm oil itself, the fiber, you're talking is about 100 million tons a year. Has not has been, if you really wanted to utilize it, and only maybe 10 to 20% has been used, but not all, because of they has to be processed immediately at the plant after the fruits has been removed from the empty fruit bunch. So this is the area where we cultivate palm oil, whereby we have like every year, for example, from June 2021 up to June 2020 is about, from January, you're talking is about 7.1 ton per hectare. They can produce the average of fresh fruit bunch per hectare. For you can imagine how many hectares we have in Malaysia. So it's a total of 5,865 5 million, 5.8 million hectare has been cultivated as far as Malaysia is concerned, and lots of the area is from the big company. So back to the biomass conversion technology, we have gone through yesterday lots of talk. They're talking about the biorefinery, from energy, for biofuel, bioethanol, biodiesels, biofuels, and biorefinery. And you're talking about bioenergy, direct combustion, cogeneration, transformation, pyrolysis. And the next one is biomaterials. So my main concern is, since I'm in the materials area, so I'm a chemist, so my main concern is on the biomaterial for bio-based products, meaning to say that after you make a direct combustion or transformation for pyrolysis, the liquid biofuels from here, we convert that into biomaterials for high value added products, okay, for this one. So back to the kenaf and palm oil, empty fruit bunch. So the chemical compositions, as far as kenaf is concerned, you will notice that the lignin is quite high. It's about 35% of lignin, with the hollow cellulose is about 50%. Hollow cellulose is the content of cellulose and hemicellulose. In all palm empty fruit bunch, you're talking about the lignins about from 15 to 30. It depends whether it is which part of that particular fiber is taken, and the hemicellulose is quite high, with the cellulose also from the lower as 23 as the higher as 65. So if you're talking about cellulose, then it's very good for you to convert these cellulose materials for high value added products. And in the lignin from EFP and lignin from kenaf is totally different, because of lignin in EFP has so high proportion of the S shrinkal unit compared to the one in kenaf. And we know that cellulose, as far as cellulose is concerned, it has the crystalline and also the amorphous region. So if you wanted to do any modification and so on and so forth, you have to disturb the crystalline area to make it more amorphous, any chemical modification. And you can dissolve cellulose by separate the microfibrils among the cellulose change with a certain solvent. So you can separate and dissolve that, and you can regenerate it back to form another kind of cellulose. And the structure of lignin is very complex, as that's why I keep asking how to make it stable, because of lignin has a lots of, you will notice, conjugated double bond, which is very active as far as UV is concerned, and will tend to polymerize. Unlike the hemicellulose, they are sugars and easily be attacked by any of fungus, fungi, and so on and so forth, because of that's make this particular materials is very biodegradable. The same as cellulose, which is made from glucose unit, but it is a very long, but it is more, because of cellulose has amorphous and crystalline area, so it is more resistant compared to hemicellulose, which can easily be extractable from the materials. So in this particular reaction, we are doing liquefaction, whereby we convert biomass into biofuel You can convert using a direct combustion, pyrolysis, gasification, and direct liquefaction. So when we're working together in Professor Zhang's lab, my student has done with the pyrolysis and also some gasification reaction there, whereby in our lab we did it direct combustion, but to make it you have to control with the temperature and times will make very crucial part here, whereby the liquefaction of biomass, you can use a solvent or certain condition to depolymerize the solvent and the biomass into micromolecules, and we know this one as a solvolysis. So you can use phenol or alcohol. The most common solvent is depend on what is your end product that you want. If you are making phenolic resin, then phenol is one of the best. But if you are targeting lots of polyol for making polyurethanes and so on and so forth, the alcohol solvent is the best as far as choice is concerned. So so it depends. So you can use phenolic derivatives because of when you use phenol solvent, it can produce a lots of phenolic derivative. And when you use alcohol solvent, you can, or alcoholysis, you can produce as many as polyol is concerned, and polyol is very important if you're targeting it to react with isocyanates and so on and so forth. So liquefaction involved with the dehydration, dehydrogenation, deoxidation, recondensation, polymerization, and so on and so forth. Especially polymerization, when you handle with lignin, it tends to polymerize because of lignin form radicals at high temperature. So that's why if you want to handle with lignin, you have to use the lowest temperature as possible. If it is not, then you have to have a certain technique so that it is not polymerized, so that you don't have so much of residue at the end of the products. So so now I'm talking about the polyol, because polyol is very important as far as functionality is concerned. The hydroxyl number is very important if you wanted to make polyurethane. What types of hydroxyl you are getting, and also the supramolecular structure, molecular structure, and molecular weight will be contributed as far as polyol is concerned, because of this will give a certain viscosity for the liquefaction products that you have. So this is the example of morphology of Knauf residue when we work with the polyethylene glycol. Okay, so we are using catalyst. Before this, we just use sulfuric acid, but now we make a combination of sulfuric acid and lactic acid to not to make it so vigorous, but to control the reaction. So with that, we can have like about 10, something about 10% as far as yield is concerned. And lots of, you will see that lots of area of lignin has been delignified, and leaving you, and also some cellulose has been degraded and dissolved in the liquefaction solvent, and giving you the residue here. And the most important part is to make residue as lower as ever, because of, you will notice that some of the residue is very high, because unlike Ulpam antifrog bunch, Knauf is very hydrophilic. They tend to, if you add solvent in the system, it tend to absorb so much solvent to make it less, the solvent less reactive to work as a liquefaction reagent. So you have to modify the process of when you're doing Knauf in this liquefaction process. For the Ulpam anti-fruit bunch is much more easier. So we make two, one using anti-fruit bunch, and the other one, the lower part, if just using the cellulose without lignin. So without lignin, you will notice that you can have as low as almost all, 0.9% left as far as yield, the residue is concerned, because of we wanted to have as much high yield as possible. And for EFB, you can get like 4% here, which is much more higher compared to Knauf. So the temperature, time, the stirring factor is make lots of contribution as far as the percentage of residue is concerned. So looking back at the XRD, you will notice that the crystalline area of whether it is knaf or whether it is alpine anti-fruit bunch has been disturbed tremendously, and it's become very amorphous to make sure that it can be dissolved. This is the what you call is the XRD of the residue, because of if you run the XRD of the liquefied, you will never see the crystalline area at all. It's all amorphous. And this is the surface structure as far as the residue is concerned, and you will notice that the crystalline area is decreased tremendously if you're measuring the residue here. And it decreased with the temperature and also with the time taken for this particular liquefaction reaction. So we also do the calculation for the OH number. So we do titration, and you have the OH as high as 300 plus for the knaf, and the ratio, with the ratio of catalyst composition with a certain ratio from 3 to 0, without lactic acid, with 3 to 1 lactic acid, 3 to 2, and 3 to 3, the percentage of residue will be reduced, and this gives different amount of what you call is the OH number. The OH number is very important because of when you wanted to make PU, so the number will contribute the properties of the PU because of how much the OH will be reacted with isocyanate in the process of making polyurethane. So for the OH and acid number for EFB, the same thing will happen. You will notice that the high temperature, you have the acid number is increased because of some of the hemicellulose open change and become acidic, become into acid, and the OH number is increasing, but then decreasing because of some of the phenol, the OH has been converted into acidic component. So this is very important to make a selection as far as temperature and time is concerned, to make sure that you have less acidics but more OH in the system, because of at high temperatures, some of the hemicellulose will be converted into acidic materials. And for the basic polyurethane, you can have like ether polyurethane base or ester polyurethane, whereby you react polyol with diisocyanate to make a polyurethane polymer. If you make a precursor of using phenol in the system, you can have a phenol derivative, so you can make a polymerization to have phenolic resin. So you can have like a diamine or diol to form urea or urethane base. So this is the global market as far as the polyurethane is concerned. It's increasing from 2016 to 2000. They expect in 2028 it's increasing because the demand for polyurethane for construction, for furniture, up to the footwear is high as far as it is concerned. And this is all using the petroleum-based polyurethane. So this is the bio-based polyurethane market in the world, whereby the Asian, Malaysia, China, Indonesia, and also the northern part of America, we are producing and also consume high proportions of polyurethane as far as market is concerned. And it's also very good adhesive as far as polyurethane is used. So what we did is we make from that system, we make polyurethane, and we managed to get polyurethane foam using water just a blowing agent, because of isocyanate. When it is attacked with water, it's relieve lots of carbon dioxide, and that carbon dioxide will be used and become foam. So you will notice that the amounts of isocyanate index, as you increase the isocyanate index, the compression strength of the polyurethane foam is increased, and later will be decreased. So we select at 120 because we don't want to have excessive of isocyanate in the system, because it is not good. And for the young modulus also, it is increased up to 130, then it start decrease. But the steep part is from 110 to 120. For that reason, we choose 120. But it depends on the end use. If you're talking about the strength, then you're picking at 120. But we are talking about biodegradability and how much water absorption and so on and so forth, maybe 100 NCO index is the best. For example, this is how the morphological of polyurethane foams look like. You have lots of foam structure, the cell structure, and the cell structure is increased as the amounts of NCO is increased from 100 to 110 and 20, then it start decreasing, and this is contributed back to the strength of that particular materials. But again, as I told you, natural fiber is very difficult to control, to get, because of the lignin itself is from even from one species to from one place to another place, from the top and to the down of the trunk, or even in the same fruit plant, the types of percentage amounts of H, S, and G is totally different percentage, even though the component is the same. So with 120, you will notice that the closed cell is about 58, and the density is about 166, which is quite comparably high. With the young modulus, quite bearable, good. Its compressive stress is about 41. It's moving by itself.
Yes, we are fine. Yeah, go ahead. Yeah, it's good.
Okay, 1 minute. Okay, so we're talking about the absorption. So this is the water absorption. So you will notice that at 100, the absorption is very high. But with the 120 and below, the water absorption is lower, which is very good as far as composite is material. But for my application, I'm interested with the highest water absorption because our end product is for agriculture base. So this is the example of PU that we made in the lab. So it's very dark color because of the lignin itself. And this is from KNAF, without just polyethylene glycol. This is KNAF at different isocyanate. So it gives you different types of foam size and the pore size. But we are interested on the 100. Although the strength is not good, but as far as agriculture pot is concerned, this is the best. So we tend to make it into pot. To make it shape into pot so that you can have a connection with the slow release fertilizer, so that we can add some chelating agent for this one, so they can chelate fertilizer for this. So we are comparing, or to make embedded cellulose hydrogel inside that using cellulose. So cellulose can be converted to cellulose 1 to cellulose 2, 3, and 4 using alkaline sensitization with a certain solvent. And the concepts of dissolution is by swelling the cellulose itself. So the water, the solvent will penetrate through and separate it. And so you can have individual fibers, long change of cellulose fiber dissolved in the solvent. And what we did is we make hydrogel from that. Okay, you have the solvent and then you cross-link and you have a hydrogel. And we did it for the growing materials, and it is very good as far as germination is concerned. So what we did is we embedded the cellulose hydrogel inside the PU. So that's why I said 100 is the best, because of it absorbs so much water, so it remains water, and biodegradability is very good. So once you use it as a planting pot, and it will degrade, and that particular plant, after it's finished, then the whole thing's gone. So which is very good. We have no waste at all as far as circular bioeconomy is concerned. So this is what we did. Planted some cucumbers with the cellulose hydrogel. With the fertigation system. So this is what we did in the lab for the smart novel growing media. And these are all of the working things we are doing in the labs currently. We even spin it into fiber. We're working this one with Yangon University for the biofuels with Professor Zheng lab a few years back. And also with Wuhan University, we're working with these membranes materials. So as a conclusion, biomass from KNAF or palm can be liquefied to make a good polyols. It depends on what number of polyol you require, and temperature times ratio of catalyst is very important to giving higher liquefaction yield. And the smooth surface residue indicate more crystalline cellulose has been degraded during the liquefaction, and both knaf and open fiber suitable in making bio-based polyethylene foam due to exceptional physical chemical properties. So I'll go back to the Leonardo da Vinci talk. They said that life is pretty simple. You do some stuff, maybe fail, but some work you do more work. You work big, others quickly copy it, but then you do something else. So the trick is doing something else, because people will keep copying, and we wanted to disperse as much as we can as far as research is concerned, and the more the merrier it is. So thank you to my research group. So who has been contributed a lot as far as this research is concerned, and I would like to acknowledge to a big grant that we received from Malaysian government for smart farming. So this particular grant consists of 3 big universities, and also a contribution from our partner members from China and also from Melbourne University. Thank you very much for your kind attention.
Thank you, Professor Zakaria. Yeah, it's my mistake. In my talk, I give a too long time and that moment for questions, but I still want to give you a few minutes for you to answer some questions from our audience. So any question for Professor Zakaria?
Can you hear me?
Yeah, I can hear you. So you can speak.
Thank you for Professor Zakaria and Dr. from Convention Funding Professor. I have one question about the the PowerPoint as well as the never have a actually connector was high. What influence about this in your research?
Did you get it, Professor Zhu? Acid content?
Yes, the chemical connector ash.
The ash content.
Yeah.
Okay, for all palm fiber, the ash content is very high because of it consists high proportion of silica. That is one bad thing about all palm fiber. Silica content is very high. So if you wanted to process into, let's say, mechanical pulps, or you want to make composite materials, it will give you high cost as far as processing is concerned, because the knife will be blunt easily. And if you want to make a pulping process to make pulp and paper, as far as chemical is concerned, the silica will be dissolved a lot in the black liquor. So during the recovery of chemical process is very difficult. So this is the bad part as far as palm fiber is concerned. But it is good as far as fire retardancy. So it is not much easily to be burnt compared to knaf, because of the high silica content. Because of it seems like it's the rush husk. There is silica content is up to 50%, I think, very high. So it's very good as far as fire retardant is concerned, but very difficult to handle because of you have so much of silica there.
Thank you.
Good, very good. Any other questions? We can have one more question. We can accommodate one more question for Professor Zakaria. If not, I have one short question for you. So we also doing some research on producing some PU-based foam for agriculture application, but our target is the open cell foam. But in your presentation, you show the SEM, those are closed cell. Closed cell is hard to absorb water because closed cell actually is more suitable for insulation purpose. Can you give some comment why you want to produce some closed cell foam rather than open cell foam?
Okay, some of the we have like Petronas fertilizer. They require a closed cell because of they want to have long-term degradation. They want it like 8 months and above, because of the cost of labor is so expensive for them to change the fertilizer every 6 months, because of due to the labor, because of the cost of labor and so on and so forth. So they want it more than 8 months, so that they want a closed cell so that the biodegradability will be there, and then it can hold the fertilizer so that it does not leach easily. That is what they want. Yeah.
slow release fertilizer. Right? So
yes,
that's
for the slow release fertilizer is very important. Yeah.
Okay, good. Thank you. So very good presentation. Okay, thank you again for the nice talk. So because the time is constrained, we move to the next speaker. Okay, so Professor Zakari, can you stop sharing your slide? Okay, thank you. Okay. So our next speaker will be by Professor Charles Jia. Charles, are you here? Charles? Okay, good. You can speak. You can speak. Open. You can turn on your microphone. So Professor Jia is come from University of Toronto, from Chemical Engineering Department, and he's a fellow of Canadian Academy of Engineering, as well as he was a former president of Canadian Society for Chemical Engineering. And Professor Jia's current research focuses more on the nanoporous structure of carbon materials for different type of application. They produce the carbon material from industrial waste, for example, from the coke or from biomass. For application including a green energy storage application, solar energy driven sanitation. So I think it's a very interesting topic today. So Professor Jia, so you can start your talk about the wood biochar as the structural application, functional material for structure for sustainability.
Thank you, Professor Xu. Can you hear me?
Yeah, I can hear you.
Very good. Let me share my screen here. Can you see my screen?
Not yet, so maybe it take a while.
Yes, I can see.
You can see? Okay.
Yes, I
can you see it now? Charles, can you see it now?
Yeah, and let me check. Yeah, I have a little bit difficulty to see that, but you can start because in my computer has some little bit trouble today.
Okay, so other the colleagues and the student can see it, right?
They can see it.
Yes, I can see. Yes, I can see.
Good.
Very good. So I would like to thank the organizing committee, particularly that Professor Zheng Fang and also Professor Xu here for the nice introduction. So what I'm going to talk about today is monolithic wood biochar, and basically that I want to make a case that this monolithic wood biochar can be treated as functional materials and in addition to traditional applications, there are other new applications. Okay. So it's not forwarding. Yeah. Okay. Okay. It's turning now. Okay. So I would like actually to acknowledge the contributions of my student first. Basically, that I'm going to present work by three people. First one is Dr. Evan Young, and another one is Randeep, and another one is Mina. So that I'm going to share their work, and also would like to take this opportunity to thank my colleagues, Professor Donna Kirk, and he's in the picture here, and also Founding Source, which is NSERC Canada. Can you still hear me? Hello?
We can hear.
Yes.
We can see.
Yeah.
Okay. No problem, right? Okay.
Yeah.
So Professor Xu already explained lots of things about the wood. Okay. So what I want to show you here is that chemically, wood consistent of, if you dry, consists of 50% of carbon. We know that those carbon from photosynthesis and extracted from atmosphere, okay? And also that wood itself is a biopolymer with a complete complex porous structure. Okay, this is actually important, relevant to what I'm going to talk about. Okay, so keep in mind that wood is a porous structure. Okay. So here is actually the biochar, right? Everybody here, I guess, knows about biochar, and we define biochar as carbon extracted from biomass via, say, pyrolysis. This can be a thermal pyrolysis, can be hydrothermal. In our case, that we only use thermal pyrolysis process, and in this case, that we use actually wood as the precursor and for the biochar. So it is well known that biochar properties are determined by biomass precursors as well as pyrolysis conditions. In the case of thermal pyrolysis, very much depending on the, precursor compositions, temperatures, and heating rate, extremely important as well. And the mechanism involved there, including thermal crackings of those biopolymers, and also that condensations, and also that rearrangement of carbon atom. So if we look at this diagram here, you can see that with the increase of temperatures and graphitic structure can be formed. Okay, and say at lower temperature, let's say lower than 800 degrees C, there will be major change in terms of chemical compositions, and the carbon content will increase. So the materials we are dealing with here actually have we produce at a temperature higher than 800 degrees C. As a result of that, they are highly carbonized, meaning that they have carbon content over 90%. Okay. So this is actually some SEM diagrams of biochar we produce, and the left panel we're looking at maple biochar, and the right-hand panel we're looking at pine biochar here. The point I want to make here is that if we pyrolyze those wood carefully, we can actually retain the macro structure of wood. What you can see here is that there are channels, a bigger one called vessels, and the smaller one called trichets, and also there's a ray. And also, if you look at the pine biochar, we also can see the pit actually controls the flow of sap between trichets. This is in the case of pine, which is a softwood. Maple, everybody knows that it's a hardwood. Okay, so what you can see here is that in softwood, we don't have actually vessel, only have trichets. So, and also if we look at the nano structures, so for crystal structures, this is actually the TM pictures of biochar produced from maple. What we can see here is that we can see some crystal structures, and based on the diffraction patterns, we know that those crystals are graphite nanocrystals. Okay, so what we can see here is that biochar itself is porous because it retains the structure of a wood, and at the same time that carbon itself is amorphous carbon and with embedded nano graphite crystals. And also that there are also differences in terms of porous structure as well. In this case, we're talking about smaller than 50 nanometers. This actually shows that this is actually from BET analysis, talking about porous distributions of maple, pine, black locust, and poplar, and biochar. What I want to show here is that with different, say, wood precursors, the micropores, which is for less than, let's say, 20 nanometers, can be different. Okay, and if you look at the say right-hand side panel here, is talking about the size of crystals, and say those are graphite crystal as well. As you can see that with different precursors, the size of crystals are different, even though that they are produced under same condition. Okay. So so we had basically some quick review of some properties of wood biochar here, And before I introduce the work of my student, let me actually quickly summarize that what is applications of biochar. Okay, so everybody knows that the traditional applications, including say soil amendment, which in terms of amount used, definitely the #1 applications. And also biochar has been used as a renewable bioenergy source, as a solid fuel, and for cooking for other purpose. And the people are looking at using biochar for steel making as well. And another application areas will be used biochar as adsorbent for water and air purifications. Okay, and there are some emerging applications for biochars, including that as an additive to other materials. For example, add to a cement, add to the polymers for different purpose. And at smaller scale, people also look at using biochar as a catalyst for reactions. So we have examples of other people doing using biochar as a catalyst for water splitting. So for hydrogen evolution from waters. And the last application actually is the one I'm going to talk about, and there's a work done by my student, and the areas use it as energy storage materials, and in the device called the supercapacitor particularly, and also that used for water purification, in this case that using solar energy for that application. Okay, so what I'm going to do now is that I'm going to share some of the work did by my student, and the first piece of work is by Randeep. He worked on the electric conductivities of monolithic biochar. Okay, and he actually pioneered this type of work, and among the first to report some of those unique properties of monolithic wood biochar. Okay. By the way, that monolithic means that the whole piece. Okay, we were not talking powders. Usually, that's a case when we're looking at other applications. So we're looking at the whole pieces of wood biochar, which basically have the inherent structure of wood. Okay, so Randeep actually studied the bunch of precursors, and including for hardwood. The hardest one will be African ironwood, which is extremely dense and denser than the water, and very light ones are boughs, and also hardwood, extremely light, and some common softwood, and also including a grass species, which is bamboo. Okay. And here is actually the reactor we tend to use that we apply. We call it ultra slow pyrolysis, and in some cases, in order to retain structure, the process can take days. Okay. Randeep actually used two different type of measurements. So one type will be 4-point method. The purpose for that is to eliminate the contact resistance, and in some cases, he also used 2-probe method there. Okay. So first, the interesting thing he reported that is elasticities of conductivities. What that's supposed to mean that if you actually apply pressure to the monolithic biochar, the conductivity actually will increase. So what you can see here is that with increase of pressures, conductivity actually increase. But if you release pressures and the conductivity decrease. He did that experiment, say, after 1 day, and he repeats that those type of property actually retained. Okay. And on the right-hand panels, he's looking at if we apply pressures, and so that we depress the piece of biochar. What you can see here is that we see the conductivity increase with pressure, and also that if the depression is over certain values and the conductivity actually decrease, is in this case that is due to the formation of micro cracks. Okay, under those pressures. Okay. Another interesting finding is that he found that the electric conductivity is highly dependent on crystal size. In this case, crystal volume here. What we plot here that is an increase of conductivities with a crystal volume. Okay, what you can see is that almost linear relationship. Okay, different colors indicates of different material here. The one point I want to make here is that if you look at the maximum measured conductivity here, in this case, that is about 24,000, which is about almost 10 times higher than the graphite direction that perpendicular to the graphene surface. Okay. Another finding is that we could anisotropic of wood biochar conductivities. What that means that the conductivity actually of wood biochar along the axial directions always higher than the radial directions. Okay, so regardless what is the precursor here, and the reason behind that is actually that is a preferred orientation of graphite crystals in those wood biochar. Okay, let me now switch gear to another piece of very nice work. This is work by Evan Young, and he actually used the monolithic wood biochar to produce we call it ultra thick supercapacitor electrodes, and the purpose is to increase the volumetric capacitance of a supercapacitor. Okay, so this diagram talking about difference between the supercapacitor and the batteries. Everybody knows the batteries and supercapacitor is less known. And the difference between battery and capacitor is that the battery can have a high energy density but low power density. On the other hand, supercapacitor have a high power density but have a low energy density. High power density meaning that you can charge a supercapacitor much faster than a battery. Okay, but as indicated in this diagram, that supercapacitor tends to have a low energy density. So the research in this area is trying to increase the energy density of supercapacitors so that it may in the future can match that energy density of a battery. Okay, and then in this case, then you will have a highly energetic batteries or supercapacitor can be charged in a very short period of time. Okay, so this is actually talking about that difference, right? And the Tesla is powered by batteries, lithium-ion batteries, because of high energy density. And but if this is actually the bus, which is powered by supercapacitor, and because bus have lots of space, and in this case, then you can charge this supercapacitor within say minutes. Okay, but only can drive 3 to 6 kilometers. And another advantage of supercapacitor is the lifespan of a supercapacitor, which is over 10 years. You can charge it 500,000 times, okay, which much longer than lithium batteries, which is about let's say 4,000 cycles. Okay. Here actually some ideal electro materials for supercapacitor. The ideal one probably will be a carbon nanotube forest, but we know that which is not practical in terms of cost of productions. So in order to have a very effective electro material supercapacitor, and the material has to be highly porous and also that highly conductive in terms of both electrons and ions in the electrolyte, okay, and cost effective. So we thought that and the biochar would produce biochar can have those characteristics. So this actually is comparison between a commercial supercapacitor and also the cell we produce using monolithic wood biochar. What you can see here is that in commercial one, the carbon materials actually is a film, okay, only about 50 to 100 micron thick, and also made of powders and say porous carbon powders. Reason for that is because of high resistance of powder materials. Okay, so they have to make it very thin. otherwise that the resistivity will be high, that the efficiency of and the capacitor will be low. Okay, because of we can make those monolithic biochar very conductive, so that we can actually use much thicker electrodes. And once we use much thicker electrodes, the packing density of those active materials in the supercapacitor cell will increase significantly. Okay, so this is the concept we want to test, if we can use those blocks of monolithic wood biochar to replace those thin films. We actually, Evan actually tried the traditional way to produce biochar, and also that another way to remove actually lignin. In this case, that we compress it, and the purpose is to increase actually density of those biochar. We call it intensified wood biochar. Okay, monolith here. Anyway, so this is two different procedures to produce biochar. One is a traditional procedure, and the one is after removing of lignins, and so that we can compress the wood and to produce high density wood biochar. Okay. Here is some result here. I will not show detail of here, and we apply the BT analysis, and also that XRD, and also that Raman to study structures. What you can see here is that those we're looking at pine wood biochar, okay, and the top one is untreated ones. The bottom one actually is compressed. Okay. And also doped those biochar with some active materials like ruthenium oxide, and to increase the energy density as well. Okay, here are some results of showing that the film structures of those doped biochar, and the distribution of ruthenium here. Okay, this is the result, the comparison with literatures, and so that with literatures of thick electrodes. Okay, what we can see here is that with intensified wood biochar, the performance actually is among the best in the published work in literature. Okay, and so this is volumetric capacitance, meaning that it's based on the energy stored per, let's say, cubic centimeter volume. This is actually a comparison in terms of aerial capacitance. As also you can see that the both top two lines is from this wood-based biochar, okay, and one is the traditional. It is actually ruthenium oxide doped, and the other one is without doping, but is only have an intensification process. Okay, so the bottom line here is that they're promising. The performance is quite promising as a result as the electromaterials. Okay, Professor Xu, how I'm doing in terms of time?
You have still 5 minutes.
Yeah, 5 minutes.
5 minutes? Okay, yeah. Wonderful. Yeah, great. Okay. So this is actually electrostabilities, and what you can see here that is after 1,000 cycles is still quite stable. In fact, that we put together another cell, we run at 10,000 cycle, okay, and the performance still as good as a new cell, which actually is not a surprise because of supercapacitor is very much a physical device. Okay, doesn't like it. It's not like batteries, and they're going to performance going to decline after a few thousand cycles. So the last piece I'm going to talk about is we also the MINA in this case that applied the monolithic wood biochar as a photo thermal materials for solar water purification. Okay, so the concept is quite simple here. So we use actually the monolithic wood biochar as a absorber of sunlight, and also that it can convert the sunlight into thermal energy. Then thermal energy drives the water evaporation. This is so-called solar absorptions, and in this case, that the light is converted into heat, so it's a photothermal conversion, and so that using visible light as a source, energy source to drive evaporation. Then we condense the evaporated waters and get pure water. Okay. There are actually 3 types of photothermal materials. One type is called plasmonic materials, which usually people use different sizes of gold particles, and then that gold particles through electron scattering process, then converts light into heat. Another type is we call it non-radiative relaxation of semiconductors, and it's more complicated. And the last one is a thermal vibration type of induced thermal vibration in the materials. The biochar actually belongs to last categories, which belongs to thermal vibrations of molecules, meaning that if you absorb visible light, the vibration of bonds within carbons will increase as a result of that temperature increase. Okay. So here are some results of evaporation rate of waters from different biochar, wood biochar. What you can see here is that we tested both, tested maple, pine, and redwood, and hemlock, and we found that maple actually had highest evaporation rate. Okay, and this actually is a comparison in terms of evaporation rate with published data. The red one is from wood-based monolithic biochar, and the black one is other lattice vibrational materials, and the yellow ones plasmonic materials, and the gray ones is non-radiative relaxation materials. What you can see here is that wood biochar are actually quite promising as a result of photocell materials for enhanced water evaporation. Okay. Here actually is we also can calculate that the light to vapor conversion efficiency. Okay, it's interesting that some of the efficiency is higher than 100%, which was a puzzle for us. But in the end, we found that the fundamental reason for that is this result. Okay, what we found that the monolithic biochar actually can reduce evaporation enthalpy. Okay, meaning that the water confined in the biochar actually needs less heat input to be evaporated. Okay, you can see that its difference is huge, and if you look at here, the bulk water is about 2,500 and 25 degrees C joule per gram of water evaporated. But if it's from biochar, it can be reduced to if it's wet biochar, can be reduced to only, say, let's say about 1,000. If it's just humid biochar, even lower. Okay, this is a fundamental reason that we can have a case that have an efficiency over 100%, basically lowers energy barrier for evaporation. So the last one, the key takeaway here is that we believe that monolithic wood biochar is a new class of functional materials and with unique properties. Of course, it's just transforming those wood biochar into a viable solution to alleviating climate change need greater effort from more people in the classroom and the students and other colleagues. Thank you very much.
Okay, thank you very much, Professor Zhao. Very nice, interesting topic. So we have a few minutes for questions. So any question from our audience? Yeah. Please speak your name. Yeah.
Yeah, Professor Jia, thank you so much for your presentation. I really appreciate the concept of monolith, which is very good. Actually, I have done something on that. And I have a quick question about the surface chemistry or the oxygen or nitrogen containing function groups of these wood biochar of your material. So I was wondering if these properties will affect the electrical chemical applications for these materials and rendering. And also another quick question about if so do you have any suggestions for choosing the precursors for these kind of biomaterial? Thank you.
Yeah, first question here is that you're talking about oxygen-containing or nitrogen-containing functional group. Yes, actually, we did some work on that as well, and that will introduce, we call pseudo-capacitance. In other words, that you are introducing tiny batteries on the surface of those carbon surface. So that will increase the energy density of your materials for sure. Okay, and also that because those functional groups on the surface and is much more accessible to electrolyte, so that the performance of that part of capacitance should be better. Okay, and the only challenge here, the major challenge here is that it's stackability of those materials. Okay, so those functional group tend not be very stable. For example, oxygen-containing group, you may those groups may be disappear. Okay, after a few hundred cycles. Okay, and you were asking a second question about precursors, and we are looking at the precursors in terms of porous structures, meaning that we want to have a higher porosity, specific surface area. We also want to have accessibility of those internal structures. So that there has to be a good combination of those properties. Another property is important actually, that is density of a biochar. Okay, so for example, that if you have African ironwood, it's very dense, right? And it's dense actually is good in the sense that your device will have a smaller volume, right? But on the other hand, if you have say the structure too dense, the internal structure may not be so accessible. So as our preliminary result indicates that actually the maple, which is very common in Canada, is among the best. Okay.
Thank you so much.
Good. Any additional question for Professor Zhao?
Hello, Professor Jia.
Yes.
Thank you. Thank you for your excellent report. I have two quick questions about the wood biochar used as supercat electrode.
Yep.
The first one is that how about the porosity of the specific surface area of the wood biochar here? And the other one is that which properties of the wood biochar make the supercat capacitance better or larger here? Thank you.
Yeah, I think you actually touched on two things, right? One is a specific surface area. It's actually extremely critical because as a physical device, the double layer is formed on the surface so that its capacitance is proportional to the specific surface area. But on the other hand, that in order for the capacitor to work, those specific surface area has to be accessible. Okay, meaning that you have to have a right combination of say macro poles, meso poles, and nanopoles. Nanopoles actually provide those specific surface area. So to answer your question, that there has to both has to be considered in terms of a specific surface area and the porosity. Okay, we can have extremely highly porous carbons like Bosa, okay, extremely porous, but porosity over 90%. Okay, but because very light, the SSA actually very low. Okay, okay. So there is a trade-off between that. Okay, and also in terms of high capacitance, as I said, that number one issue will be accessible specific surface area. Okay, you want to have as high as possible specific surface area, which meaning that maybe over 1,000 square meter per gram. At the same time, that has to be accessible. Okay, another way to increase capacitance is introduce other functional group like the previous gentleman mentioned that oxygen and the nitrogen group. And in our case, that we tested the other oxides, ruthenium oxide, which is very effective.
Okay, thank you very much.
Hello.
Hello. Yeah. So everyone in the room, we are back, right? So we can continue our conference here. So I apologize again for my bad time control so we have some delay, but I hope we can stick to the schedule now. So here I want to introduce Professor Zhang, Professor Ruizong Zhang from University of California in Davis. Professor Zhang is a fellow of American Society of Agriculture and Biological Engineers. She has many years of research experience, effort in the area of bioenergy and biomass conversion and also biochemical production. In terms of the research, she also worked on the waste treatment as well. She has been a co-founder for many startup companies, which is very impressive to me. And she also received many prestigious awards, including the environmental award from US EPA. So I think I want to give the stage to Professor Zhang. So if you are ready, you can start to present your work on the conversion of food, agricultural waste into bioenergy and byproduct. Professor Zhang, the floor is yours.
Okay, well, thank you so much, Professor Xu, for a very kind introduction. And
can we see a slide in the room? Okay, so now we can see that.
You see the slide? Okay, good.
Yeah.
Okay, well, again, thanks for a very kind introduction. And also thank you to Professor Fang for inviting me to give a presentation. Hello from California. Very nice to meet you. And I am with the UC Davis, University of California, Davis. And so I'm from Department, oh, sorry. Oh, okay, so I'm from Department of Biological and Agriculture Engineering. And today, so my presentation includes 2 parts, and bioenergy and bioproducts. Bioenergy is going to be focused on the biogas energy, and bioproducts will be focused on biofertilizer products and bioplastic products. Oh, something's going on.
Can we see the slide? Can we see a slide in room in the on site?
Can you see it?
Yes, we can see.
Okay, so go ahead. Yeah.
Okay, so my 2 parts: biogas energy, biofertilizer, and bioplastics. So my laboratory at UC Davis is called the Bioenvironmental Engineering Lab, B-Lab. So we conduct research, develop technologies for converting various food, agricultural waste, or residues, byproducts into bioenergy, biomaterials, and biochemicals. And speaking of food waste, first, food waste is a huge problem, and globally, and in the United States, China, all other countries. So food, there's a report that shows about 1/3, 30%, over 30% of food produced from farm, and so put on to the table, it's a lost. Okay, so 30% of food produced is lost as a food waste. And so there's a lot of resources, labor,
and money put into food production, but over 1/3 of it is lost as a food waste. And so there's an urgent need, there's a lot of need for reducing the food loss, reducing the food waste, and for food products that cannot be consumed, so they need to be utilized for converting into high value products rather than put it into landfill. So most of food waste is, food waste is a disposing landfill or just the land applied without any treatment, and creating a lot of economic, environmental problems. So food waste include food residuals, leftovers, food processing byproducts, and also, besides food waste, there are a lot of biomass and agricultural byproducts, including animal manure, straw, different types of straw, and even some algae produced from the nutrients from the wastewater. All of these are good bioresources that we can utilize as a feedstock for producing energy, biomaterials, and biochemicals. So what my presentation is going to be about is more about the bioconversion technologies. Previous speakers were more about thermal conversion, some chemical conversion. So my presentation is more about the bioconversion technologies. So I'm going to start with anaerobic digestion. Anaerobic digestion is a process where we use a mixture of microbes, and that include bacteria, archaea, even some fungi, working in a very well controlled oxygen-free anaerobic environment, and so that can convert organic waste, okay, so anything biodegradable, quickly convert into biogas. And so the leftover after biogas produced is called the digestate. So digestate include solids that are residual, and the nutrients, fibers, water. And so this one is nutrient-rich liquid solids that can be further processed, utilized as fertilizers or as a raw material that can be used for producing biochemicals. And the biogas contains 50 up to 80% of methane, and that can be readily used for heat, power generation, can be also cleaned up, processed into natural gas, into compressed natural gas or liquefied natural gas, and it can be also further converted into gasoline and into chemicals. So biogas is a valuable gas that can be further processed, utilized for various uses. And the biogas utilization has been largely applied in commercial levels, and internal combustion engines and electric fuel cells. Okay, fuel cells. So these are for electrical power generation, and so can be just burned directly. Can be burned directly for heat generation, and certainly, so these are compressed natural gas vehicles that can be used to just take in the renewable natural gas produced from biogas for fuel. So all of these are commercially available. So utilizing food agricultural waste for biogas and also converting digestate into fertilizer products has many benefits. It diverts organic waste from landfill and produce energy and various products, and also could have the digestate put into soil and as a high value soil amendment, and certainly it has environmental benefits. It captures greenhouse gases and other emissions that otherwise would be emitted. So in the United States, there are about 2,300 facilities that use nerve digesters, and most of digesters are in the city, and most wastewater treatment plant in the cities have nerve digesters for treating sewage sludge. And so there are about close to 70 digesters treating food waste, and so about 650 or so, or a bit higher landfill projects, and so about the 300 nerve digester on farms. That number is increasing very fast. And because there's a lot of interest, initiative, incentives provided by the government to work with the livestock, especially dairy, swine farms, to build the digesters. In California, in the past 7 years, there has been huge development of nerve digesters on dairy farms, because there is a new regulation that requires dairy farms to reduce methane emissions from manure by 40%. And so that's that requirement translated to a lot of action, and dairy farms need to really utilize the technology, for example, nerve digestion, to treat the manure. And also state government, California government is providing a lot of funding and to help dairy farms to build the digesters. And so in the past 7 years, from since 2015, and the state of California has provided over $200 million and as a cost share, normally about 50% of total capital cost, as a cost share to support 130 anaerobic digesters on dairy farms. So these are new, just new development in past several years. And most of digesters are covered lagoon digesters, because dairy in California, dairy farms use water to flush the manure into lagoons. And so covered lagoon digesters are the most common digesters on dairy farms. Here's just an example of covered lagoon digester on this farm. There are 1,200 dairy cows, and the biogas is collected, put into engine generator for generating electricity. So engine generator has 600 kW capacity. So here just the okay, and but the majority of nerve digester biogas projects on dairy farms process biogas into renewable natural gas. Basically, what it does is collect the biogas and remove moisture, remove iron sulfide, remove some organics, then passes through methane and purification system equipment to produce renewable natural gas. Here's one example. Okay, here's a dairy farm, and I use covered lagoon digesters, and biogas is collected and processed through this biogas cleanup and purification equipment. These are membrane filtrations, use membrane separation to separate the methane from carbon dioxide. The methane is collected and stored and used for these vehicles. So these are renewable natural gas vehicles that are fueled by the biomethane produced from dairy manure. So that has been very exciting. And so that program has been going very well, and more funding is made available this year, and also it will be made available next year, and to help more dairies to produce, to build more digesters. And my own research, I have been working with the digesters for many years. And so I I have been leading a project called UC Davis Biogas Energy Project, and with the funding from government, industry. So it's an alliance between university and the industry and the government. So with the objectives of research demonstration of digestion, biogas conversion, biogas energy technologies for converting various organic waste into biogas energy, bio-based products, and also provide a lot of education, outreach activities, so that people get to know more about the biogas energy technologies, and also and help industry to adopt the new biogas technologies. Okay, so these are just some of the sponsors of this project. And one of the technologies developed in my laboratory that has been scaled up and commercialized through our biogas energy project. So this is a technology called high solids anaerobic digestion technology. It's a thermophilic digestion, and so it's a 3-stage and 2-phase. So it means waste is digested first to convert into volatile fatty acid, and then volatile fatty acids convert into biogas. So the system designed to treat a variety of organic solid waste as a co-digestion or as a and a single stream. And so because of high temperature, thermophilic digestion, and also bioreactors designed in such a way, we can have fast degradation rate, shorter retention time that translated to smaller digester tanks, less cost, and have a high quality, high throughput of biogas. And because of thermophilic digestion, 2-phase digestion, we're able to destroy any pathogens that come in with the feedstock. So we can produce digestate that is safe, pathogen-free, and has a nutrients that can be used for fertilizer products. And so this technology has been has gone through research, demonstration, and also we have commercialized the technology. And about 10 years ago, I helped I was a co-founder of a company called the Clean World. And that's when we took the technology from the pilot scale to commercial scale. And so we have developed the 3 larger facilities using this high solids anaerobic digestion technology. One is for our campus of UC Davis. And so this anaerobic digestion facility is designed to process or treat 50 tons per day food waste. And so it's on campus, and so it will provide us with a lot of opportunity for research and also for education outreach. Okay, so here's just a photo of this facility, which that is called UC Davis Renewable Energy Digestion Digester facility, REED. Okay, so this one has 4 tanks. Have 4 tanks. These are 3 in the back are thermophilic digesters. And so here's a digestate storage tank. And so these are 3 digesters are connecting series, and the feedstock come in and clean up and also ground and then put into this first tank. That is a hydrolysis acidification tank. And so in this tank, the material is degraded, converted into volatile fatty acid, then transferred over to the second tank where high density population of methanogenic organism methanogens are housed to convert the volatile fatty acid into biogas. The third tank is a polishing tank. Whatever is not digested is digested over here. And the biogas is collected from these 3 tanks, put in, going through this pipeline, and then cleaned up And this is a electrical power generation station. So here's a hydrosulfide scrubber, and here's a moisture removal by chiller. And then so here's a activate carbon for removing some organics. And so then we have 4 microturbines with the 800 kilowatt capacity, so to generate electricity. The waste heat is partly used for generating more electricity. Waste heat also collected to use for heating these digesters at a thermophilic temperature. Is about 50 to 55 degrees Celsius, so thermophilic temperature. So it's a year-round stable operation. And here's just some details about the various equipment. I'm gonna to skip this one. And types of material coming in as a feedstock. Majority is this one. It's the food. Sorry. It's a food waste from grocery stores and some food waste from food processing plants, and also food waste from restaurants, source-operated food waste. And here's ice cream from dairy processing. So we receive over 10 types of food waste, food processing waste of various types. But in general, and on a weekly basis is about 50 tons per day of such material processed in this facility. Okay, so with that facility, we are continuing with the research to improve anaerobic digesters in order to increase the efficiency and lowering the cost. And so we are, so I have been working with my students. So basically give the challenge, we need to further reduce the digester size by increasing the rate of reaction, and also improve the digester control. And so monitoring processes and integrating digesters with the upstream, downstream processing technologies. Okay, so what is downstream? Downstream is to utilize digestate as a valuable resource for producing organic fertilizers, nutrient-rich organic liquid solid fertilizers, and also we can use that one for producing other products as well. So this is a digestate, has nutrients and micronutrients, has 3 to 5% solids content, and so also has live active microbes. And so that's okay. And so we have been, developing various types of biofertilizer products, solids product, the liquid product. And so here's a liquid product put into drip irrigation for tomato production. And we have developed the integrated processing technologies to take a digestate through solid separation, membrane filtration. And so this concentrate that contains most of microbes and the solids, and we further dry to produce this pelletized fertilizer, and so liquid further concentrated to put it into the drip irrigation for tomato, other plants, food production. Okay, and so we also produce the algae, microalgae from digestate, using the nutrients from digestate. Then we harvested the algae for biodiesel production, and also for adding algae biomass back into digest for more methane production. And so we've been looking at the other products from microalgae as well. Okay, so and here's another project. Right now we have been working on the past several years to produce biodegradable plastics, utilizing fermented food waste and some food waste that are rich in sugar. So we use this organism, halophilic Mediterranean, and to produce the PHA. Okay, so what is a PHA? PHA is a polyhydroxylate, which is a highly desirable bioplastic material and fast growing, expanding in the bioplastic market, and has properties that are close to thermoplastics that can be used for manufacturing various types of biodegradable plastics. That's higher value than polylactic acid, PLA bioplastics. So our research has been using the food waste and other food processing waste as feedstock for producing PHA. And we have developed the technology for taking in the waste that we anaerobic ferment to produce fatty acid. Then we cultivate the cells to produce PHA. Now we harvest the cells, extract the PHA for biopolymer production. So here's just the process of food waste ferment. So here's a PHA produced from the food waste. And then we also have been researching the PHA production from cheese waste, cheese byproducts, like the lactose permeate lactose powder. And so I'm here just showing you the cells production using the cheese waste as a feedstock. And so we've been working on both batch and continuous fermentation. And here's a PHA produced from in our lab, and from food waste and from cheese waste. And so has 80% HB, 20% HV, is excellent biopolymers that can be utilized to make a plastic film or form the products like spoons, forks, packaging, food packaging material. And so currently we are in the process of optimizing and scale up PHA production, and also moving into producing some food packaging and food service products using the PHA produced from my lab. And then with that, I wanted to acknowledge my research staff and postdocs, graduate students, undergraduates, and also have a lot of industry partners working with us, and certainly government industry funding agencies that have been supporting my research program at UC Davis. With that, I will stop. Be happy to answer questions if you have time.
Thank you. Thank you, Professor. Thank you. It's a good timing, so time control. So we have time for questions from audience or from the room on site.
Okay, thank you.
Hey, Professor Zheng.
Yes.
Okay, thank you for your excellent presentation. I'm a master from the Biomass group, so I have a simple question. So you mentioned in the USA, the dairy biogas could generate $21.1 million value, but in China, in some small farmers, it couldn't equip with the expensive digestion size. So my question is, could you give me some suggestions about China's dairy biogas development? Thank you.
Oh, okay. Yeah, thank you for your question. First of all, that $200 million, so that's government funding and provided to dairy farms to build the digesters. And so each dairy digester typically costs about $3 to $5 million. And state, California, provides 50% of it, so like $1.5 up to $2 million for dairy digester. So that's government funding, not the cost of dairy digesters. But so to your question, then dairies or livestock farms in China, and so yes, I have worked with the some farms, some biogas projects in China as well, and so worked with the Qingyuan, the DQY, and for a large biogas plant in Badali. So we actually producing that facility produce biogas from chicken manure, and so also passing through membrane separation, producing renewable natural gas. And so China has a lot of opportunities, and so but again, cost is an issue, and so normally anywhere. Because of the electricity, energy is still cheap, and so the cost of digesters are really high, and that's why a government needs to provide some funding, and also we wanted to, if we can create value from digestate, for example, high value fertilizer products, so that will help improve the economics for digesters, and definitely China has a lot of opportunity and for developing biogas projects.
Okay, thank you very much.
Thank you.
Very good. So any additional questions?
Hello, Professor Zhang. Can you hear me?
Yes.
I'm Zhang Huan from Funds Group. Thanks for your excellent presentation. And I'm very interested in the REACH biogas project you have introduced. And I wonder whether it is feasible to set up such kind of biogas project in China, in some university campus or residential sub-districts. Actually, we have made some surveys of the waste production in one of the campus of Nanjing Agriculture University, and I think there are some supporting factors in South China, including the moderate winter temperature, the high population density, and the lacking of central heating systems, and I think biogas projects like the READ project is very promising, and I want to hear your opinion on the feasibility and the key factors and all the expected difficulties in setting up such kind of projects in China.
Yeah, thank you for your thoughts, comments, and also question. And I totally agree with you. And China Agriculture University could be a leading campus for building, developing such a biogas, bioenergy project like what we have done at UC Davis. The best thing about the developing project at the university is the model. Is a technology model, business model, and then get a lot of attention. People come to see it. That's a part of education. And so I think it's doable, like what we did. It took a lot of effort. And but what my experience is, it takes a private public partnership. Okay, so university has a land, university has technology, but we are researchers, we are students, faculty. We need a private partner, strong private partner to work with us and design, build, and even operate such a digester in order to sustain. So this is not our digester is a full-scale digester, is not the research digester. It's a full-scale means it's going to operate year-round and has designated staff to operate. It's not like just research project, and then when the funding is out, done, we're done, so we have to shut down. So our campus digester actually, and it's a year-round, fully staffed operation. However, the whole facility is automated, only have 2 people operate. And that's good about when we build this digester is a high-tech digester, so that allows us to collect a lot of data, and it's fully automation. And so only one person manage a facility, another person just bring the truck, direct the trucks to put the feedstock into the digester. And so that all of those need to come into place together in order to really develop a large scale, full scale digester. But certainly you could, before this full-scale digester, I developed a pilot digester, 5 tons per day. That was a research digester. So after I got enough data, I shut down, I used for research, but this larger scale 50 tons per day digester is a full-scale stable operation digester. It will be, has been great model for, the public, for university.
Thank you very much. And I also have another question. I mentioned I noticed that you have mentioned the pathogen-free digestate. And I want to know how to produce the pathogen-free digestate and what is the key measurement measures?
Excellent question. One is the temperature. So thermophilic digestion is very effective. Okay, thermophilic means 50 to 55, close to 55 degrees Celsius. So just the thermophilic digestion is very effective in destroying the pathogens. And so in our case, we also have 2 phases. The first phase is a low pH, high acid, organic acid. In that environment, so combination of acid environment and high temperature, thermophilic digest temperature. So basically that's where pathogens are destroyed. So we did the tracking, and so that's a combination of that environment is very effective in destroying any pathogen that come in from food waste or other other material that in the feedstock. So I think it's not difficult in that regard if we use thermophilic digestion and acidic environment.
Okay, I have learned a lot. Thank you. Thank you very much.
Thank you for your interest.
Very good question. Any other question from our audience? If not, I have one small questions regarding the PHA. So Professor Zhang, so you produce PHA, which is very impressive to me. So those are bio-based plastic materials. Have you have some data to share, for example, about yield and also the purity of your product? Those will be just if you think you're able to share. If not able to share, some confidentiality is fine.
No, I'll be happy to share. And so I thought I didn't have time, so I just went through very quickly the yield. So we actually have a papers published, and I'll be happy to share with you. And but in this case, just this graph, I didn't have time to go through in detail. And so here's the yield. Is about 26% of lactose converted into PHA. Okay, so if you work with the volatile fatty acid, there's about 32% of conversion. So 32 to 35% of conversion from volatile fatty acid to PHA. But based on the sugar, in this case, lactose, 26, close to, this is just one number, but we have a range. Yeah, so just the ballpark is about 30% conversion.
Very good. Yeah. How about purity? The purity of your PHA?
Yeah, purity. That's also a very interesting question. So for both for PHA produced both from lactose or sugar, and also PHA produced from fermented food waste, which is volatile fatty acid. The purity is really high. So we have done because here the cells, these are pure culture. These are pure culture, and so it's pure culture and extreme halophiles. Okay, so we don't. That also is important. So we're able to maintain pure culture, and so now we harvest the cells. Now we do lyse the cells, extract the PHA. And then so PHA has a high purity, and so we have done some GC analysis with the HBHV. And so we don't have to do extra or additional purification. So it's pretty clean, pure in that regard.
Very good. Thank you. Thank you for sharing those interesting results. So if no question from the audience, we will.
Professor Xu.
Yeah.
Can I have a very short question?
Yeah. Sure.
Okay.
Go ahead. Yeah.
Okay. This is Zhang. Professor Zhang, many thanks for your very nice presentation.
Thank you.
Particularly, I impressed by your commercial plans. My very simple question is, in States, any commercial plant for biohydrogen production?
Oh, yeah, that was a very question. Very good question. I did a lot of work on the biohydrogen, and biohydrogen, we actually from our two-phase digestion, biohydrogen is produced from the first stage, and so acidification, that's where biohydrogen is produced. But in our case, we directly pipe the biohydrogen into our second phase. So we are only getting methane, we're not collecting biohydrogen. And so also my experience has been in this batch feeding operation is very important for biohydrogen, high yield biohydrogen, and compare with the continuous feeding. And we do produce biohydrogen, but we're not collecting as a hydrogen. We actually just convert biohydrogen into methane in our case. But the biohydrogen is important in the product. In our case, we have not, in the United States, there's not much need for biohydrogen. And so there's a lot of development for hydrogen. We even have a lot of development plans for hydrogen highway, but that has not taken off because it's pretty much replaced by electricity. And so electrical vehicles rather than hydrogen vehicles.
Thank you very much.
Yeah.
Okay. Thank you.